Good afternoon. I'm Tom Gardner, a member of the Silicon Valley Technology History Committee and organizer of today's webinar. Our committee organizes events, now webinars, to capture the history of technologies originating in Silicon Valley. Lockheed actually predates semiconductors in the Valley and arguably is responsible for the Valley. Today's webinar is our third on Lockheed's contributions to the Valley. If you'd like to learn more about our webinars, go to www.siliconvalleyhistory.com. 31 years ago this Friday, the Hubble Space Telescope was launched and has been orbiting the Earth every 95 minutes, about 17,000 miles per hour, and is still working today, 31 years after launch. A telescope is a complex system that isn't much use if it can't be continuously pointed in the right direction, repeatedly, held steady, and in this case, serviced for repair and upgrade. That was Lockheed's mission and the subject of this webinar, the Hubble Space Telescope. We're not going to spend too much time on the lens system and the 5 instruments, but today instead focus on the design and control of the spacecraft. We have 3 veterans from Lockheed today. They have over 100 years of experience with Lockheed. They will walk us through the Hubble spacecraft history, starting with a background. We'll then go into detail on the pointing control system. We'll discuss integration, test, and launch, and then the post-launch checkout and summary, and finally go into Hubble product. Our first speaker is Jim Carlock. Are you there, Jim?
I'm here. Thank you, Tom. Thank you for putting this on and doing all the work to get everybody going here. I'm Jim Carlock. I came to Lockheed in 1967 as a control systems engineer and worked on a variety of different space ground systems, all related. Then in 1987, I became the program manager for the Hubble for the last 3 years of the development contract. The history of the Hubble, a lot of people point to a paper written in the late 40s by Dr. Spitzer advocating an orbiting observatory and laying out a lot of the arguments for why that would work. If I fast forward through the start of the US space program, the formation of NASA, some earlier smaller observatories that were launched. Then in 1977, a lot of work by NASA, along with the science community and the industry partners like Lockheed, to define what a space telescope should be. There was a competition for who would build the various parts, and we won the spacecraft portion. And in 1977, Congress authorized funding, and so we started in late 1977 to work on the telescope. Most of this presentation will focus on the time between the start of the funding and the final checkout and completion of this development contract in 1990, since this is the work that was done here in Sunnyvale. And between 1977 and 1989, we were designing, building, testing, and 1989, everything was completed. We shipped the telescope from Sunnyvale to Kennedy Space Center. As luck would have it, we shipped a few days before the Loma Prieta earthquake. We had to get the telescope at Kennedy, set up again with the test equipment, verify everything had survived the transportation and was ready to launch. 1990, the shuttle Discovery launched the Hubble and was on orbit. By the end of that year, all the initial checkout of all the ground systems and the flight systems were completed, and our development contract ended. 1993 was the first of several planned servicing missions. The plan was every 3 years or so to go back to the shuttle, to replace any failed parts, to upgrade technology as it came available, and to also boost into to make up for the drag. The Hubble itself has no propulsion system. As Tom pointed out, we just passed 30th anniversary last April, and it's still operating today. Now, there's a lot more detail on what Hubble has done on the NASA sites, specifically the Space Telescope Science Institute and the Goddard site. What Lockheed brought to the table to work on this, we had a lot of experience building and testing large spacecraft and operations support. We had the facilities that were already built and checked out to accommodate large spacecraft, and thermal vacuum, acoustics, and so on. We had a lot of experience integrating these optical payloads, not Hubble, but others. And what we did, of course, the facilities were available, and we brought test teams from some of these other programs who were able to hit the ground running. So there was a risk reduction. Another capability we brought was a history of precision pointing control, which was definitely a heart of the Hubble. While it's a totally different control system that we'd used in the past, we first team over who could bring all that experience to bear. To help with the pointing control system, we had an already developed flight computer that we could use. And also the electronics had been developed that interfaced with this flight computer, another risk reduction for the program. This flight computer, you would say, would be primitive by today's standards. It took about 1 microsecond to do an add and had about 24 kilobytes of RAM memory. The computer box had redundant power supplies, redundant CPUs, and some redundant memory for long life. Some of the new requirements for Hubble, of course, it had to be serviceable by a suited astronaut. All the electronics and other boxes had to be replaceable on orbit. While we were used to doing testing in clean rooms, we had to go one better for Hubble, class clean room to preserve performance in the ultraviolet. So everybody had to have bunny suits, full bunny suits to work on this. The third thing that was new to a lot of us was that since the Hubble was totally unclassified and NASA did like to publicize all the good work, we were expected to deal with public relations and the media. The initial setup for the program, it was a combination NASA and ESA program. ESA brought the solar arrays and one of the 5 scientific instruments. There was also the independent mission planning and science operations, the Space Telescope Science Institute on the campus of Johns Hopkins University. They were the interface with the science community and did the mission planning, which was then passed on to Goddard to actually operate the spacecraft. Goddard and others brought the other 4 science instruments. Our contract was with the Marshall Space Flight Center in Alabama. There were 2 contracts, one to Lockheed to build the equipment section and to do the system integration. One to PerkinElmer to do the optical telescope and find guidance sensors. And of course, NASA Kennedy was launch operations. NASA Johnson was the shuttle operations and also the home of the astronauts. So what was our responsibility? We had to do the equipment section design and development, and that's pointing control in the flight software, structures, the mechanisms, and the thermal control. We had to do the command and telemetry systems, the communication systems and antennas, and the electric power system, except for the solar arrays. All the individual pieces were designed, tested, sent to the assembly, along with all the hardware from the other contractors. This was put together, tested, including environmental tests, and shipped to the launch base for launch operations. We had to make sure, our responsibility, make sure that everything fit with the ground operations, with the shuttle, with the astronauts as far as servicing, and with the launch base operations. Just some facts to put it in context, the Hubble's nearly 50 feet long, a little over if you open the front aperture door, weighs about 25,000 pounds. A typical operation takes about 2,000 watts of power, maybe 2 microwaves worth. The back end is about 14 feet in diameter. And the LIN, the telescope, for you camera buffs, it's about an F-24 system. As I mentioned, this is just a cartoon showing that the Hubble design had to be capable of servicing. And you can see not only did you have to provide handholds for the astronauts, you had to provide doors that they could open, and each of the components had to be removable and serviceable. So in summary, we had some risk reduction things between our proven facilities and the proven computer, and we brought experienced teams to bear. Now, the next two speakers will bring some of that experience here. They were there from the beginning of the proposal all the way through launch and support thereafter. Dr. Hugh Dougherty will be the first, and he'll talk about the controls, which was the system that was most tied to the performance of the spacecraft. Many have used gyros and reaction wheels before, but nothing to this level of accuracy. He had to do everything to millionths of a degree. So I'll turn it over to Hugh.
Thank you, Jim. It was a great presentation. The control system was my responsibility from 1975 to 1989. I came back and worked on it again when we had the solar ray disturbance effect. And then when I retired, I worked for them for 3 years, helping the ground station. So Hubble is considered to be a cosmic time machine because it allows the system to point anywhere in the sky that the astronauts want us to go. So let's look at the picture up in the right-hand corner. There is, I put in a coordinate axis because it makes it easier to talk about it when we have some axes. So the V1 axis is along the bore side of the telescope looking out towards the sky. And the V2 and V3 axis are in the focal plane of the telescope. So all the images are formed in the V2, V3. We point with the V1 axis. So looking down at the sketch here, the little cutaway, the light comes in through the telescope. The telescope has a field of view that's plus or minus about 1/4 of a degree. It comes back into the primary mirror. It bounces from the primary mirror up to the secondary mirror, comes back through the primary mirror, which has a 16-inch hole in the center of it to allow the light rays to get through. And it forms an image back here at the focal plane of the system, which is 4.5 feet behind the primary mirror. So you notice all the electronics, the science instruments and so on are clustered around that point. So what you get at the focal plane is a picture just like your camera takes. And so no camera gets the whole picture. So the whole picture frame is divided up into pieces. The wide field planetary camera, which is down here below, is called a radial instrument at the minus the V3 axis here, gets the primary portion. It has the center field of view. It's got 160 by 160 arc seconds field. The axial instruments share the rest of the annulus around that, and the outer annulus of the picture, because it's a circular image, the outer annulus is shared by the fine guidance sensors. So the fine guidance sensors, they have between about 10 and 13.8 arc minutes, and the V2, V3 axis is the focal plane. So the way the fine guidance sensors work is they look out through the telescope and they are sharing the image that's off axis. And so they give us the information of how much to change the pointing to put their image right on perpendicular to the bore side of the telescope. So now in terms of the pointing, we have to do jitter to 0.007 arc seconds. So let's just talk about what an arc second is. A circle has 360 degrees in it. The idea then is like a clock has a circle face and has 12 hours in it. So the circle, each hour is broken up into 60 minutes and then 60 seconds. So an analogy with that, what we do is take every degree and break it up into 60 arc minutes because it's arc on the circle. And then each minute is broken up into 60 arc seconds. And so if you multiply 60 times arc seconds going around a circle, the RMS, with the requirements not plus or minus, because even though the telescope is moving up and down, we really have a number that's what's called RMS. So you square the values that you get between the plus and minus. You take the mean over like a second, and then you take the square root of that, and that is the requirement. It'll be a positive number. So that's about 2 millionths of a degree. We have to return to the target within 10 milliarc seconds. We're going to talk about milliarc seconds because to go into 0.01, so it takes a little thought here in terms of everybody looking at it. But this is essentially 10 over 1,000. So 1 over 1,000 is a milliarc second. And so therefore you get, that's also RMS, and that's about 3 millionths of a degree. So now let's get back to the control system part, the vehicle. So there's 5 parts to it: the aperture door, which you can see up here in the right-hand side too. And then there's the high gain antenna, which is pointing to the TDRS satellites up in synchronous orbit. And then there's the solar array. And then there's the Lockheed bus, which is basically this frame around the telescope. And then there's the telescope assembly inside. So now how does Hubble work? So there's a reaction wheel inside of here. And by conservation of momentum, when you spin the reaction wheel, the vehicle spins in the opposite direction. So the vehicle is obviously very large. So it has the dominant, what's called moment of inertia. Moment of inertia is its resistance to being accelerated angularly. Just like when you step on your scale, your mass on the scale is the acceleration, the resistance to the acceleration of gravity. And so that gives you your weight. So the same thing here, we have a moment of inertia, which is its resistance. And the telescope also has its resistance, its moment of inertia, which is its resistance to acceleration. So now you can see we have to get the reaction wheel into this vehicle. So it has to fit inside here. So we have a size, weight, and power constraint on the system. The method now that we're going to use is we're going to size, and we'll talk about in the next thing. We're going to size the reaction wheel so that we can maneuver the vehicle at a rate that's compatible with what needs to be done in the system. The second thing that needs to be taken care of in a thing is the structural stability of the system. The control system cannot stabilize modes if they're in its bandwidth. And bandwidth is about 1 hertz, 1 cycle per second. And the solar array then has to be put, since you can't stiffen this up, it just has a boom. We put this about 10 times lower than that at 1/10 of a hertz. Well, that takes care of the stability problem, but what it introduces now is a problem that we can't put in steps into the system because that will excite the solar rays and they will start to oscillate. And we're only allowed 1 milliarc second for the solar ray jitter. So that means we have to have a very smooth profile in the system. Talk more about this in a minute. The system then also has the optical telescope assembly inside of it. The optical telescope assembly attaches with the main ring, and Cliff's going to show you this picture later with the primary mirror inside of it. So the main ring then attaches to 3 points to the spacecraft. This is the stiff section of the spacecraft. The back end here is just a cap, a sheet metal type cap, and this is another, just a cap covering it. So all the strength in the vehicle is here in the system support module. You can see how thick it looks in terms of its support. So there is the attach point. It turns out, since the reaction wheels are in the bus, the Lockheed built spacecraft, and the gyros and star sensors are put on the optical telescope to get the best image we can, the best jitter. It is right close to the focal plane. So we're on the underside of the optical bench, which holds the 4 axial instruments. And we make that 18 hertz because it turns out that it's more difficult to stabilize it when you're in 2 different bodies. So there is other equipment on board. There's 7 sun sensors, for example, to make sure the sun doesn't get in the aperture door. We have 2 sun sensors on either side to close it. So now, how well is the control system doing? Well, this is the on-orbit budget we have for it. We have 4.5 milliarc seconds that we've allocated out of the 7 milliarc seconds for the control system. So this is the 3-axis jitter before they come up with servicing mission 4, which is the last mission in 2004. And the gyros and the RMS basis are looking like this, okay? We're nominally meeting the requirements. It's still a little above here. But there were only 3 gyros left in the mission. So they had to replace the gyros in order to keep the system going, and hopefully into like it's going now for 30 years. So when they put the new gyro in, you can see when the gyros are working better in this phase. So they're running down about 3. So we're handily meeting that requirement. So then we have to figure out what are the design two requirements for the reaction wheels and the gyroscopes. So I've capitalized the ones that are given to us by Marshall Space Flight Center, which was the center that directed the telescope. So the science then, we have to track Halley's Comet at a rate of 21 degrees per hour. So that means that we're going to set the gyro is going to have two modes. It's going to have a science mode and a maneuver mode. So we're going to set the gyro so that it can measure this. And so we set its rate at 30 degrees an hour. Well, like we mentioned before, there's 12 hours on a clock and there's 360 degrees. So in 1 hour, you move 30 degrees an hour. So the hour hand on your clock is 30 degrees an hour, which is the rate on the gyro in the science mode. We have to maneuver 90 degrees in 18 minutes. So since we're going to have to shape it, we can't use a constant acceleration. But if we go with a constant acceleration, just to get the bottom, the least acceleration I could have for 9 minutes and then decelerate for 9 minutes, it takes about half of this value. The rest of the value on the acceleration is due to the fact that we need it for torque and we need to have it for controlling the other devices on orbit. This turns out to be what's equivalent to 10 microradians, which is 1/100,000. I haven't talked about a radian is, but a radian is you take a circle and you divide its circumference by its radius. So the circumference is 2 pi times the radius divided by the radius. You come out with 2 pi, which is just a number. And so if you're going to do calculations, you have to have a dimensionless angle. And so the 2 pi around the circle is the same as 360 degrees, which is the same as 1.3 million arc seconds. So therefore there's an equivalence. And so we can turn it into this dimensionless angle. And so now if we want to know how much torque does it take to do this, well, the moment of inertia, the resistance of the telescope, the body to being accelerated is 80,000, and the acceleration we want to put on it is 1/100,000. We multiply the two together, and we come out with 0.8 of a Newton meter in the SI system, the International System of Units, which is what Marshall wants us to work to, or it's 60,000 slug foot squared in the British American units. They're all still the same ideas. It's just who has what measuring stick when you go to making it. The torque then is 0.8 Newton meters or 0.6. And so we're going to put a 12-bit digital to analog converter to drive the wheel. That gives us roughly 2,000 plus and 2,000 minus increments that we can divide this into. So you can see that we're going to have a minimum torque capability of about 0.4 of a millinewton meter. So it's going to be a very fine torque quantization we can give it, and that keeps the profile real smooth to keep from exciting the arrays or anything. So now we get back up here. If we have to set the vehicle so that the inertia of the moment of inertia times the rate of the vehicle plus the moment of inertia of the wheel times its rate is going to be equal to 0. So we're going to have to fit the wheel inside the telescope. So we're going to use, since we liked 1/100,000 here, we're going to make the inertia of the wheel 1/100,000 times smaller. So now it's going to be like 0.8 of a kilogram, or it's going to be like 0.6 of a slug foot square. So as you can see, the way you make a precision pointing vehicle is you take a very massive object like the Hubble and you tickle it with a feather to get it to move. So we've everything we can do is 100,000 times smaller than whatever the inertia and so on of the bigger vehicle are. So now we have to figure out, we're doing the smooth torque profiles. We use 1 minus the cosine type shape waves. The jerk is the derivative of acceleration. And so we integrate the first jerk pulse and we get ourselves up to acceleration. The second jerk pulse stops the acceleration and we go to constant rate. And so now we got to figure how much do we have to do in terms of meeting the power requirement, the 500 watts. So we have to design a wheel that meets the 500 watts. Now up here in the right-hand corner is the Hubble. You can see the solar rays up here. Hubble is a battery-dominated system. So everything is run off the batteries, just like the cars and your cell phones and things like that. And the solar ray, all it does is charge. So we can only charge during the daylight, can't charge at night. And so therefore we have to make sure we don't draw more out of the batteries than they can replenish with the solar rays. So we're allocated 500 extra watts to doing the maneuver, the quiescent power in the reaction wheel is about 45 watts, which takes care of all the DC to DC conversions and telemetries and commands and so on. So now with 500 watts and 2 minutes it takes to start the acceleration and stop it, you can work out that this turns out to be, by conservation of energy, the 0.2 degrees per second. So if that's true, it's 0.22 degrees a second, and we've designed the inertias so that the ratio is a 1 to 100,000, then the reaction wheel speed has to be 100,000 times greater than this. Okay, so we're now going to make the reactions wheel speed 3,000 RPM. Okay, that if this is in rotations per minute, if we take 60 and divide it in, that'll give us rotations per second. And like we said before, cycles per second is a hertz. And so that says we can go 50 hertz. This rate here requires that the vehicle go to 22 hertz for its maneuvering capability. Now we made it larger because it turns out that there are external torques on the vehicle. The gravity gradient is trying to straighten the wheel, the vehicle out, so it points towards the earth. And so we have to fight that it's trying to overturn us towards the earth. There's also error torques that are hitting the system, and they come into cyclic terms as well as a steady state term. So the wheel now is sized to absorb all these cyclic terms and to hold a portion of the inertially fixed torque coming from the aerospace, from the aero density. The magnetic torque system, which is on the vehicle, that is used to fight the external torques. It's basically the wheel in absorbing the torques will increase its wheel speed. And the momentum, the magnetic control system, what it does is it uses the wheel speeds to drive the wheel speeds to a lower value, and it's leaning on the vehicle all the time. So the vehicle has to have enough torque to overcome the torque that's being pushed on it so that it can desaturate the wheel also. And so now we've got the different rates here. We go up here and look at the budget. We have 4.5 milliarc seconds. So the gyro is used for angle as well as rate. It's an angle gyro, integrating gyro, which means its output is incremental angle. And so we're going to make the incremental angle about 1/20th of this, okay? So that says that we're going to make it 1/4 of a milliarc second, which in terms of microdegrees is like 1/10 of a microdegree. So now we have the parameters set up for the gyroscope. In maneuver mode, we have to set the rate on the gyro. It's 0.22 degrees per second for maneuvering, but this is also the same gyro we use to capture the in safe mode to get to the sun as fast as we can. And so we've upped this so we can have a little extra capability to get to the sun quick, because again, we're living on the batteries. And if you don't get to the sun, the batteries will deplete too much, and that would be not a good situation for the system. And then the pulse weight, since this is a 1/2 degree a second, that's 1,800 degrees per hour, and this is 30 degrees an hour, the pulse weight goes up by a factor of 60. This next chart then tells us what the structure of the PCS is. The Space Telescope communicates through the high gain antenna to the synchronous altitude tracking and data relay satellite. Comes down through the 1 megabit link to the antenna on the ground. And so the ground has two major components, which is the Science Operations Control System called STOC, which is run by Goddard. And they are basically managing the vehicle. They are responsible for its health and welfare as well as the science. The science people are pushing to the scientists to get in their data into what they want to do for testing. And so they send in their proposals, and then they decide which ones they want to do. And so they're usually doing this 1 or 2 years ahead of time. So we need a system where we can provide the capability for people to pre-program all their activities into the system. So now, in terms of the structure, the uplink commands coming up on the PCS is we break it into 2 parts. There's a time processor, so they send us up time-based commands. These are the commands that tell us when to turn a box on or when they want to do a maneuver. And then there's a conditional processor, which allows them to do decisions to decide which path they want to go to. It allows branching, it allows circling, it allows different kind of operations. So the way that works is that the science instrument and the fine guidance sensors have a success, no success flag that they pass to us, okay? So if we ask, for example, the fine guidance sensor to go out and find a guide star, and it doesn't find it, it comes back with no success, and then we go to the next guide star pair. Similarly, if the science instrument finds out that when we move them to where they want to be, it wasn't exactly where they wanted to be. They come back with no success. And then if they've programmed into it, we'll move to the next position that they would like us to go to. The capability of the scientists to work at real time exists. So there is a system, the station in the Goddard stock, and there's a thing at the Science Institute. So if they put a timed weight in the conditional processor, they can be running the vehicle real time. But as I mentioned before, nothing gets into the vehicle unless it goes through our command generator so we can shape the profiles of the system. So let's talk a little bit about a second about this. So this is the block diagram of the system, the control system, a generic diagram. So this is the spacecraft. This is the vehicle with the solar rays and the all the other structural modes. And then that is the sensor. So the sensor basically is the fine guidance sensor when we're locked on to the fine guidance sensor, or we generate attitude with the gyro. So the gyro has the pulse weight, and so we can integrate pulse weights, add them up, and that'll tell us what the angle is. So we have this can provide both rate and angle during the maneuvers and other times that we need things like that. The actuator is the reaction wheels. The magnetic torquers are only used for the magnetic control system, but it has similar kind of structure to this. And so the actuator then is driven by the compensation in the system. So we have a pretty standard PID controller, proportional integral derivative. It has about 12th order worth of filters in it. It has saturations and switching lines. The idea then is that it's average 1 minute's worth of data. We're getting data out of the fine guidance sensor at 40 hertz. That's the rep rate on the control system. So we're calculating every 25 milliseconds, sending a command out, and it puts in the error here. And then the system, basically, this is what the gyro measures. And so out of that, it figures out what's the bias error that it's not getting, because this figures out what the DC bias is on us for us as it changes versus time. Now, one thing is the quarter of a milliarc second here would saturate the reaction wheel torquers. So therefore, you cannot drive the system with the angle error. You have to have another path, and that's the accelerator. Just like in your car, you want to go faster. Well, you come through the accelerator and you tell it to give me this acceleration, and it goes right into the reaction wheel. So the speed of response for the system is totally due to the acceleration. This is basically an error correcting loop that we have on the system. There's other modes changes that you can have in the system, so you can change the gyro gains and the like. Programmable commands. All right, so we have a programmable command structure that provides the ability to pre-program science operations. The constructs are the software language they have in the conditional processor stored. And so there's a whole group of them here, which are mainly for the scientists to use, so they can use they'll tell us what branch operation, they can time the branch operation. The branch operation is if the instrument tells us they had a success or failure, that tells us which one of these paths to go down next to do the operation they want. If they want to somehow delay it for some reason, then they have the ability to do that also. There's some commands for the ground to initialize our pointer and get the vehicle time set and so on, coordinate with them. This one here, the one-way word memory load, is used for the system to change gains in the system or whatever needs to be done. There's a group of telemetry tables, and they can pick which ones they would like. The fine guidance sensor has commands, which is mainly the logic, so we can lock it up. And then there's the vehicle commands, which we've talked about before, so we can do maneuvers. So now looking over how that works. So the stored program command, which is on hard time, typically is used to turn on the units. So there's 3 fixed head star trackers, and the star trackers, they pick 1 or 2. There's a 31 command. So out of this list of constructs, we have an onboard interpreter. So when it sees a 31 command, it knows what you want to do. It looks into the fine guidance and says, okay, you want these 2 processed, I'll do it. And then it puts into the processing for the software. But even though it's processed the data, it doesn't get into the control system unless someone sets up a 45 command that tells us which sensor they want to use. So a lot of times the fixed head trackers might be just used for an attitude update at the end of the maneuver. And then what we do then is if it's an attitude update, we leak that in through the command generator to correct the attitude. The fine guidance sensor there's 3 of them. 2 of them are used for the for controls. It's going to be 2 and 3 because they've dedicated the fine guidance sensor number 1 for astrometry, which is basically measuring the angle between stars and galaxies. And so 2 and 3 is our choices for selection. So they can put up commit. They want 2 of them, or they just want 1 of them. If they want 2, then we process 2 guidance fine guidance sensors. The brightest guide star is acquired first, because that makes it the easiest one for us to acquire, because we have a brighter object in the sky. There's an X and a Y inside. We'll talk about that in the next other chart. But the V2, V3, each one of them generates their information relative to the tilt, the rotations from the V2, V, and 3. So once we know what FGS it is, we can rotate it in the proper frame and bring it into the focal plane of the telescope. So the first thing it does, it goes into cost track. And then we'll talk about that in a future thing. If we don't hold it back, but here's the logic commands we have. They tell us all the logic. If they don't want to hold, if they want to let it go through, it just drops through autonomously, goes into fine mode acquisition. Now, once it's done all the logic and checked it, and we've checked it to make sure it meets the angle constraints between the guide stars, then that can be placed into the control system. There's the observer we kind of showed before on the other one. The controller has 5 gain sets for the science mission, so they can select which one they would like for the kind of operation they do. The momentum management system we mentioned was the magnetic torque, is what takes in the speed of the system and desaturates the wheels. The high gain antenna is a broadband beam on it, so we can just be open loop pointed by the ground. They give us that. Similarly, the solar mover, they have their own shaping on their command so that they don't excite our the solar array that they provided to us. All right, so now the reaction wheel and the gyro. The reaction wheel is the device that you see here. This is the housing of the reaction wheel that's bolted onto the frame of the spacecraft. This is 24 inches in diameter, 20 inches high. The inner rotor inside the thing is this clamshell looking rotor. The stator on the motors and tachometers are fixed to the housing. So when the housing gets bolted in, it fixes this. And now we have a motor that can turn inside there on these bearings and rotate the wheel. The wheel is 19.5 inches in diameter. In red here, we've shown that's got the tip mass, because that's where all the inertia is going to be pretty much put into the system. The imbalance in the rotor, because that is one of our concerns, is the imbalance in the rotor is going to potentially excite the structural modes, but we've balanced them to 4 microinches, so there is no such pot that it's not going to excite anything. So there's a lot of been work done on balancing the wheels. This is the 1-time spin speed, and this is the 2-time spin speed. This is the 2.8, which is the bearing retainer. Now here's the bearing. The retainer force is the phenolic thing inside the gyro, inside the bearing, I should say, that holds the balls in place. So you can see we're way down into the mud because these are just little phenolic things. And then the bearing terms of these are due to the raceway defects. Again, it's just the raceway defects for these bearings, which are ground to be an ABEC 9, which is the best bearing you can get. And so therefore, these are relatively benign numbers as far as I was concerned. The way that the reaction wheel works, as we mentioned before, it's not holding any one speed. This is holding one speed so they can get measurements for a test in the suppliers. But the reaction wheel is actually moving up and down, and it probably doesn't get much above 10 hertz during the science mode, because that's the level that we're going to get from absorbing the gravity gradient torques and the cyclic torques that we get, plus whatever residual we have of the inertial fixed torques. So we typically are in this region down here. And again, the telescope, the primary mirror is probably in this region here, and the secondary mirror is in this region. So essentially, they're at very high frequencies. So the only time we can ever get up there is when they do a maneuver and add 22 to this. So 22 would be the number for the maneuver, and then it would go back another 10 or 14. So it could be in this, it'd be 1-time spin speed. So it would move that up to a higher value. And again, it would just be a real small number, and it won't excite the bearing, the structural modes. So the rate integrating gyro. This gyro, as we mentioned, integrates means it puts out the integral of rate, which means that it puts integral angles out. We've mentioned before that the integral angle is going to be, its resolution is 1/4 of a milliarc second. Okay, so here's the box. This is the box that the astronaut comes up and replaces when he puts the gyros in, we're going to hear about later. So the box has two precision drilled holes in the bottom, and it mates to two precision pins on the Perkinoma section, the optical bench. And then the astronaut can come up and replace it to arc seconds of accuracy. So what's in the gyros? The gyro essentially has a mount in the box. When it's in the box, by the way, there is a heater. So the gyros are all kept at 160 degrees Fahrenheit, and that's to stabilize the parameters in the gyro, like the magnets and the fluid that we're going to talk about. So now here's the main housing that contains the float assembly, and then it contains some torquers and so this end is the signal generator. So the way the gyro is going to work is it's going to start to rotate. So here's the spin axis, here's the spinning axis. So the wheel rotates around. H is denotes angular momentum. So it rotates around. It's a ceramic rotor. It runs on a ceramic path. It's a gas-filled gyro, 90% helium and hydrogen rather than 10% helium, and it's going to be lifted as soon as you turn the motor on and start spinning it. It lifts off there and it starts spinning around. Now the gas was coming out before and causing turbulence, so we've put a shroud on it to get the noise in the gyro down. The reason we're getting the noise to the gyro is not that it affects the jitter or line of sight pointing or anything like that. What it does is it saturates the reaction wheel. When you have a really small torquer, in order to just put minuscule forces or torques onto the Hubble, then it doesn't give much dynamic range for the gyro noise to come out. So we have a fifth order filter on the gyro, plus we've knocked this down. So basically now the gyro doesn't have any risk of coming out anywhere near saturating the reaction wheels. All right, so now we got the angular momentum, we understand that. So the thing is, the float is constrained. It's a magnetically suspended system. So it's constrained to only rotate around this axis, okay, which is called the output axis here. So this is the spin axis, this is the axis it can rotate around. So this has to be then the input axis, spin in out. It puts the omega cross times this way, and the output axis is the axis we're going to torque around. So for the gyro, the output axis is our torque axis. We're going to put a torque on this to resist the rotation caused by the rate vehicle, the input rate with the angular momentum. So now with this float can move, a pulse is going to be worth in this gyro, it's going to be 1/8 of a milliarc second. So what happens is the rate goes in and the gyro integrates that rate, and when it hits a signal here that tells it it's up 1/8 of a milliarc second, it comes down and gives it a torque to reset it to 0. So every time it starts to rotate up, it gets reset to 0. The clock inside here that's doing this is 300,000 kilohertz resetting on this thing. And this gives us a lot of precision. So we mentioned before, the readout is twice of that. That's because of the way the readout electronics works, but the gyro never forgets anything. The gyro has all the information, even though we might have read it out with a factor of 2 on small signals. It's going to say, you didn't take the right number out, and it'll keep giving us the number back, and eventually it'll average out to what it tells us to be averaged out to. Let's put this thing, this is typically, so the measured rate then is the torque over H, but since we're getting incremental angles, we therefore know what's happening. Here's the fine guidance sensor. The fine guidance sensor, let's talk about this path. So what we're looking for in the fine guidance sensor, here is the guidance star that it's looking for. What it does is the wavefront, we're pointing off. So this is the bore side of the telescope, and the guide star is at an angle to it, okay? And so its wavefront is coming in at an angle. And so the whole idea of the fine guidance sensor then is to find out what angle it takes to make our bore sight perpendicular to the wavefront coming down from the guide star. So the tilted rays are coming down in here. It goes into the pickoff mirror. So let's jump towards this one now. So here's the fine guidance sensor as a physical piece of hardware. It's 5.5 feet long. It's about 3.5 feet wide. And the telescope rays are coming in here into the pickoff mirror. As we mentioned now, all the units, radial units, are sitting there with arms on them that have to reach down into the photograph, because it's taking a circular picture. That mirror then reflects it back up and it hits the aspheric collimating mirror, which is the pickoff mirror, goes up to the aspheric mirror. This is going to try and take the telescope spherical harmonics out, and it also collimates the line of sight, the rays. So they come down back through the star selector servo. So this is star selector A. I put a little V1 here because this then has to be optically aligned with the telescope. Okay, that's what, even though it doesn't physically look like it's in that direction, it's optically aligned in this direction. So this is a very important alignment, because this is the alignment then that determines how well we're going to do. And it goes through this star selector servo. It's a 21-bit encoder. It's motor driven, and it has a 9-inch through hole, and the motor is a 10-inch bearing on it. So the torquer that's on this motor is 4 times the torquer on the reaction wheel, because they have to get this system up to about 200 hertz in order to overcome the bearing friction. And then also in there, each of the Risley prism, inside each star selector server, is a Risley prism, which offset the light rays into a 7.1 arc minute cone. So coming out of here, the light is coming along the V1 axis, but by the time it gets out of the star selector servo, it's on a cone that's got 7.1 minute arc, 7.1 arc minute radius. And so that's coming down into here. And this now sits on the cone that's coming out of the other one, and it creates its own cone. And we'll talk about how this goes in a second here. Then it comes down to the star selector, and it goes through the filter, the band, it goes to a beam splitter. The beam splitter takes half the energy, sends it this way, half the energy, sends it that way. Now, internal the coordinates to the fine guidance sensor, because they're fixed in the box, and then the box is calibrated relative to its mounting fixed point in the vehicle on an optical bench. And then we know where they are, and so we can rotate the X and the Y back into V2 and V3, because what we're looking for is the tilt of the focal plane, and the focal plane is defined by V2 and V3. And the way it's kind of defined is that's what they're looking at. This light is coming in right off of the focal plane assembly. It's about the focal plane image. The image is about the size of a pie plate. So we are looking at the outer rim of pie. So it goes up here, it splits it, and now it goes into what's called a Kester prism. It's a split prism. And so light goes in, and this just obviously is flooding the face here, but it goes through, and then the photons on this side will go out to the photomultiplier tube here, and then the photons coming through here go to this photomultiplier tube. Photomultiplier tube is such that when the photon hits the surface, it's got a semiconductor surface on it, it kicks off a photoelectron. There's about 2,000 volts across the photomultiplier tube. So it accelerates that down and hits the base, and the base then turns it into an electron that goes in to drive the electric circuit that counts the photons. So both of these are photon counting systems. Both of them have a 5 by 5 arc second square field stop. So all that the photomultiplier tube can see is a 5 by 5 arc second square on the sky. So now this is an interferometer. So with the wave, or the calculation for the interferometer, is the A pulses minus the B pulses over the sum of the pulses. And that's what's called the S curve. So now let's see what the S curve looks like. So this is the signal in the S curve, and you can see that the linear range of the interferometer is plus or minus 20 milliarc seconds. In other words, it's the tightest thing that we have to meet, even though the pixel in the wide field planet camera is 40 milliarc seconds. There's nothing as tight as this. And this is the one that we have to make sure that they and the PCS are in sync here. So we do guide them. We give them a command signal to move them so they don't have to move themselves. They have a control system that's about 3 times, 4 times faster than ours, but it's not fast enough to keep out of trouble. And so they have to keep it really in here. So we have to hold them tight. Now, this is the S curve. Ideally, the magnitude of the S curve should be 0.7. but it's not quite there. But you can see they're getting a fairly good curve. And so this is not angle. So to get angle, Perkin-Elmer gives us a fifth order polynomial with calibrated coefficients they picked up in testing. And then that allows us to turn this signal into the interferometer output. So the signal coming out of the star selector, the fine guidance sensor, is the star selector servo angles, and it's the interferometer signal. So from that, we can figure out where they are in the plane and get the errors from them. So now, how did the FGS acquire stars? Well, as he mentioned before, there's optical arms due to these star selectors, and they, at the end of them, they have 5 by 5 arc-second fields of view. Now, it's kind of an exaggeration because this is really about 10.2 arc minutes, and this is about 13.8, and this is 250 arc seconds across, a little better than 3 arc minutes. So this is a very small aperture compared to the overall size of the Perkin-Elmer fine field of view. This is often called the pickle because of its shape. And so what the ground does is the catalog, the star they want to go after, the catalog tells them where the star is to about 1 arc second. And then we're going to have an error due to the maneuver, due to the drift in the gyro and the star selector servo, the gas factor and so on, so that we have to have some play in here so we can place them. And then they are able to scan out. So they initially start here, even though I show the field here, but keep it distinct, I pull them up. So it starts up here where it thinks it is, and then it's going to go in a scan, and it does that. And how does it know where it actually is? Well, it takes the sum count out of all the Fulton multiplier tubes, because if you take A plus B out of both of them and add them up, then that is actually the magnitude of the light that's coming through. And so that gives them the magnitude measurement they need. And so if it meets the magnitude that's loaded into the uplinked command load that people gave us in the conditional processor, then they say, I've got it. And so they say, I got the star. And then they immediately go into around the star. Now, again, it's only 5 by 5 arc seconds. And what they're trying to do is create an equal light path at each corner of the square. And when they think they have the light path equal, then they know that's in quotes the centroid of the 5 by 5 arc second square. But they still haven't captured fine lock. But they want the fine mode to get that fine pointing on the interferometer. But that captures the centroid. And then if the ground doesn't tell us to stop them from moving down, they will autonomously go into trying to acquire the interferometers. Now, this interferometer signal extends across the whole 5 by 5 arc second. So there's an X and a Y that extends across the whole region, but it's only 20 milliarc seconds wide. So they have to find that 20 milliarc seconds. So they step back because there may be alignment errors, and they have the diagonal moving 6 milliarc seconds per step. And so this is 20 milliarc seconds plus or minus. So they look for 3 counts that look like it would be something that looks like this shaped curve, okay? So as they're coming in, they would see 1 count, 2 counts, 3 counts, and they would say, okay, this looks like the interferometer. When they do that, they capture it to this interferometer. That's their plan. So the fine guidance sensor then directs them to null out the interferometer. And so the fine guidance sensor is their nulling instrument to push them into the center of the system. Now, once they acquire one fine guidance sensor, one interferometer, they're up high. They haven't found the other one yet. So then they just kind of walk down that interferometer signal until they hit the next interferometer signal. When they hit another one, they capture to that. When they've got both of them captured with the star selector servo, they send a command to us that they've captured it. And then they go on to guide star 2 that we've stored. We give them that. So in the next in the next field of view, there's another fine guidance sensor next to it. And so it goes into the same process. It has 2 guides, or has a guide star, maybe a backup guide star. And the system is going to acquire it. When they acquire a star, and this one acquires a star, they tell us we've got both of them. The commands come back to the software. The software looks in the command list and sees what should the angle be between those two stars. And if the angle is incorrect, it rejects it. In the conditional process, it says failure. It says no success. and therefore they'll go on to the next guide star pair if someone's programmed that into a branch statement. But if it meets the angular criteria, then they drop into the fine pointing mode. They tell us we're ready now to give you information, and we start using these fine guidance sensor and process it for the data. So now, how well does the system do? Well, here's the ultraviolet coverage of the Hubble Ultra Deep Field in 2014. Now there's been a lot of field using somewhat similar data and just compiling it as time goes on. But the new part of this one is it's doing the ultraviolet. So one of the advantages of Hubble is it has a ability to capture ultraviolet levels as well as going down into the infrared. Now the Webb telescope, which is in process now, it's an infrared telescope. So the hope everyone has is that Hubble will keep going so that it can make dual images, one with the Hubble, which will get them up into the higher region, the ultraviolet region, and then they can get complementary instruments. So here's the field of view. The field of view of the wide field planetary camera is 160 arc seconds square. To put this in perspective, it would take 24 million of these pictures, 1,000 square degrees, and this is about 2,000th of a square degree. And so it takes quite a bit of these pictures. So Hubble is basically a surgical instrument that goes up and sees an area of the sky that the scientists all agree is a very important information, so they can either test their theories or come up with new ideas or whatever. And so this is the picture we take. Now we're holding it to 7 milliarc seconds. So we're holding it to 7,000ths of an arc second, which is like 1/6 of a pixel in the wide field planetary camera. And then we do overlay images from orbit to orbit. We overlay that to within 10 milliarc seconds, which is a quarter of the width of the pulse in a wide field planetary camera. So when you see these dots of light, we're holding the lights on a pixel pretty well. And so this then gives them the opportunity to get the brightness they need, and the same thing for the spectrographs. We're holding them very accurately, so they're getting the information they need to know about the spectral composition of the stars. So this provides the information for drawing these kind of ultimate ultra field things. So this shows 1.3 billion light years within a few millions of years of the Big Bang. It's a constellation in the southern hemisphere. This is 841 orbits of Hubble. It's also augmented by some of the data from the infrared experiments and the close-in mapping satellites. There's 10,000 galaxies in it. As you mentioned, Hubble's UV capability filled in the period from 5 to 10 billion light years when most of the stars were born in the universe. And the way that the Hubble gets the good UV capability is in the coatings that are on the primary mirrors. So the primary mirror has 3/millionths of an inch of aluminum, but if it was only aluminum, UV would get absorbed by the aluminum. So they cover it with 1/millionth of an inch of magnesium fluoride. And then that ups the UV capability to 75% transmission, and it only degrades the aluminum down to about 85%. So now they're getting a good throughput for both UV and the optical regions that they looking at it lower towards the IR. I said, how'd they do that? Just kind of a little repeat of what we talked about before, is do the flexible commands constructs allow them to do repeatable orbits. And during the initial observation, if they know that that's the star field they want to come back to, like for example, they have visited this one many times, and they say, I would like to go back to the same star field. So they put in a command load that they would like to come back. The FGS star select, the servo settings are saved by us autonomously. And then there's software settings that we use. We do velocity aberration calibrations. We do lots of corrections to the system as well as our own inertial information. So that allows them to come back for future observation. And as we said before, we'll replace them back within 10 milliarc seconds. So now in summary, the PCS design met all the requirements. The flexible control system and the command structure lets them to pre-program both the Science Institute and the ground station operations for as long ahead of time as they want. That way they have everything in a can ready to go as time goes on, and again, the stock decides whether the vehicle is operational and whether it should get the commands. And it's a joint science institute stock decisions to make. All right, now post-launch, the control system provided the attenuation of the solar ray torque disturbances. The reason that there were torque disturbances is on the side of the solar rays, there are booms that extended, and these booms were not thermally coated. They didn't have any covers on them. So the situation was that when they came out from behind the dark into the light area, the sun hit one boom faster and longer than the other one, and that allowed the booms to distort unevenly. And when they did that, they got a torsion, and there was a spring mechanism up here that had a lot of stiction and friction. And so in the process, then they weren't able to get the torque down. So we had to design something that would reduce the torque. So just roughly 75% of the 95% of the orbit was not usable, and only 5% was. And when we put the fix in, which was to put in basically two 6-order filters, one that would wrap a loop around the torque source itself, the vehicle that had no motion on it, and then the other 6-order filter essentially canceled it out, so the existing system didn't know it was there. So when we pulled it out, it didn't change anything for the people who were designing. It was pretty transparent, and therefore, when we put the filter in, it gave them about 95% of the capability of the science back, and they lost only maybe 5%. So post-launch, we did the backup gyro, we being the stock, and I supported them on that. The design using it for a 1 gyro, 2 gyro system. The system, the 1 gyro and 2 gyro system can't do science, but it can do maneuvering. And so that's the idea. The gyros maneuver with the help of the magnetic field. So they have a magnetometer. We carry a 9-dipole model of the field on board. And so they can tell what the angle error is, and they can use that then to put it into our control system to drive the loops, okay? And so it doesn't actually have a rate signal, but we could put a lead network on it and turn it into a rate signal. And then post-launch, they also replaced the TF224 computer with an Intel 486 32-bit computer. So now I'm going to introduce Cliiff, who is going to talk about integration and test and launch.
Hi, Hugh. The design of the pointing control system continues to allow astronomers to make amazing observations after 31 years. I started on the Hubble program the day that Lockheed was awarded the contract in October of 1977. My first assignment was performing test planning and test requirements. I then became manager of system engineering organization that was responsible for designing the systems, the shuttle crew system design requirements and the systems test requirements. I then went to an organization that audited the test plans of all the various program hardware. Starting in 1983, I was manager of the Hubble assembly and test. I went to the Cape with the Hubble and was on the pad when the shuttle bay doors were closed 3 days prior to launch. I'm going to talk about the assembly, test, and launch of Hubble. Next chart. Mil-Spec 1540 establishes the requirements for environmental and structural ground testing of space vehicles, launch vehicles, and their subsystems and units. Lockheed and Sunnyvale had all of the test facilities required to perform the testing of shuttle-sized space vehicles required by this spec. Prior to Hubble's assembly, all boxes, mechanisms, and subsystems were tested as required by the mil-spec. Hubble was assembled and all ambient functional testing was performed in a Class 10,000 clean room. Environmental test facilities were used for the acoustic, thermal vacuum, thermal balance, and the EMC test. The assembly of the Hubble equipment section started in early 1983. In the summer of 1983, we started functional testing of the equipment section. The telescope and fine guidance sensors were installed in the Hubble in late 1983 and early 1984. Perkin Elmer was then able to start their testing. As the scientific instruments were delivered from Goddard Space Flight Center, they were installed and functional testing was started on them. Next chart. This is an image of the primary mirror. The mirror was 2.7 meters in diameter. And you can see on there the image of the technician standing by the mirror. And that shows the 2.5 magnification of that mirror. The mirror is mounted on a main ring, and you can see 3 white attach points there. That main ring was what was used to attach it to the telescope assembly itself. The cover over the mirror opening is used to prevent contamination of the mirror structure. Next slide. This image shows the metering truss being assembled to the equipment section. You can see the telescope at the top of the image, and then in the middle you see the equipment section bays, and at the bottom you see the optical bench, which has railings and latches for the scientific instruments. Neither the forward nor aft sections of the vehicle were installed. That would be done later in the process. Next slide, please. This shows the Hubble in the work stand and a support stand in the work stand in the Class 10,000 clean room. The support stand can rotate 360 degrees to allow access for installation and maintenance of the various parts of the vehicle. The wall behind the Hubble is a bank of HEPA filters. Behind those HEPA filters are 3 huge fans that continue to blow air through the HEPA filters, provided Class 10,000 clean air laminar flow throughout the high bay. Next slide, please. This shows the Jet Propulsion Lab and Lockheed technicians installing the primary scientific instrument, the Wide Field Planetary Camera. There at the bottom right side is the technician controlling the crane that was using to be installed the vehicle, the scientific instrument. Next slide, please. Functional testing was designed to test each subsystem, including the fine guidance sensors and the scientific instruments. Tests were performed to verify the correct operation of the hardware and software. During the test, all the commands were sent to the telescope and the response is verified. Test designers created a Boolean equation logic model of Hubble, including the expected telemetry responses. Test segments were then written and simulated using the logic model. Once a segment was successfully simulated, files of the commands and predicted responses were created. The tests were then performed, and when a response that failed the expected response occurred, that was printed out so that it could be analyzed near real time. Functional tests that were run in ambient environment required many manual operations to install and remove simulators and to make mechanical measurements. An ambient functional test that were run before and after each environmental test took approximately 2 months to perform, working 24 hours a day, 5 days a week. Next chart. Environmental testing that was done included the acoustic test. The acoustic test was performed to verify that the Hubble would survive the launch and ascent environments. During the acoustic test, the vehicle was subjected to 135 dB for 2 minutes. The next test that was performed was a thermal vacuum thermal balance test that verified that Hubble would perform spec in space and verified the thermal math model. Functional tests were performed at the hottest and coldest predicted in orbits. Simulated mission operations were performed. The vehicle was put into a steady state configuration. Thermodynamicists monitored selected temperatures. When these temperatures stabilized, a number of temperature monitor readings were used to verify the thermal math model. A modal test was performed on the Hubble structure. Modal survey testing is a form of vibration testing where various points are stimulated by stimulators. The object of the test is to determine the natural frequencies, shapes, and dampening of the vehicle structure. The test had to be performed from midnight to 5 a.m. to assure that there was a minimum of street and highway noise that could affect the test. The EMC test was performed in an anechoic chamber. The test verified there was no electromagnetic interference with the electronics on the vehicle. The Space Telescope Operations Control Center at Goddard Space Flight Center sent orbital operation commands to Hubble. Both the Space Telescope Operations Control engineers and the data analysts in Sunnyvale analyzed to verify them. Verification of Hubble interfaces with the astronauts and shuttle were performed by analyses and by inspections. Astronauts used their tools to verify various interfaces with the shuttle to be sure that they could access the equipment to be removed and reinstalled. Neutral buoyancy tests were performed at Marshall Space Flight Center and Johnson Space Flight Center in large water tanks. Mock-ups of pieces of hardware of the Hubble were put in the tank, and which allowed the astronauts to verify the interfaces. Next crew, please. This shows Hubble in the acoustic cell. When Hubble was moved to the various environmental test facilities, it was moved from the work stand onto a transportation dolly, then moved to the appropriate facility. Then when Hubble was moved to the acoustic cell, the upper part of Hubble was wrapped in plastic to keep the optics clean. Note the transportation dolly has no wheels. There's pads at the bottom of the dolly that are air pads that lift the vehicle and the dolly and allow it to be moved smoothly over rough land floor. After installation in the acoustic cell, the cell doors were closed. The test was performed. It was then returned to the clean room and a functional test was performed to verify the vehicle had survived the environment. Next chart. The thermal vacuum test. Lockheed has several thermal vacuum chambers that were able to accommodate shuttle-sized vehicles. The one that we chose to use was in a high bay adjacent to the clean room that the Hubble was in. This chamber, the back of the chamber is a cold wall that is cooled to almost absolute zero, allowing the chamber to be pumped down to the equivalent of 100 nautical miles. There are heat lamps line the cold walls of the chamber. These lamps are turned on and off to simulate the sun shining on various sides of the vehicle. Next chart, please. This shows one of the astronauts in Sunnyvale working on the stand, verifying his tool would interface correctly with the equipment that was going to be changed out in space. Next chart. This is an image of an astronaut getting ready to do a neutral buoyancy test. And this, you can see it's a very large tank. They were about 60 feet in diameter and about 20 feet high. The astronaut was, you can see red straps around his legs. Those were putting weights on his legs, and he also had them around his waist to make him neutrally buoyant. Then mock-ups of various parts of the Hubble were put in the tank. The suited astronaut was lowered into the tank, and then they were able to perform various tests. You can see in this particular one that the astronaut is installing the simulation of a mock-up of a wide field planetary camera. Next chart, please. This is Hubble functional testing was scheduled. Hubble was originally scheduled to be launched in 1984. Due to design and test issues and a 2-year slip because of the Discovery disaster, launch didn't occur until 1990. The pre-ship test functional was completed in August of 1989 in the Sunnyvale clean room. Hubble was then shipped to KSC in early October of 1989. Fortunately, that was about 2 weeks prior to the Loma Prieta earthquake. Hubble was shipped using the shuttle transportation system. The shuttle transportation system was developed by the government to ship shuttle payloads from their manufacturing and test facilities to their launch site. The system consisted of two C5As, one carrying the payload in the shipping container. The other was used to ship the various pieces of equipment required to load and unload the payload into the shipping container and move the shipping container into and out of the trailer, transfer the equipment to the C5As and back to the to the launch site facility. Once Hubble was installed in the class 10,000 clean is 100,000 clean room at Kennedy, another functional test was performed to verify that it had survived the transportation process. Hubble was then installed in the shuttle cargo bay in January of 1990 and transported to the pad and made it to the booster. The first launch attempt was made in March 25th, 1990. The launch was aborted at T-2 seconds due to a booster problem. The second attempt was made April 23rd, 1990 and was successful. Next chart, please. This shows the shuttle being lowered onto its dolly so that it could be taken out of the high bay and loaded into the shipping container. Next chart. And that's the Hubble launch. Next chart, please. In conclusion, Hubble was successfully tested in the environments it would have to be operated in space. The in-orbit maintenance design to allow astronauts to perform servicing operations was demonstrated. Control of the Hubble by the Operations Control Center was verified, and all of the math models were verified by testing.
Okay, Cliff and his team successfully assembled and tested the Hubble. It was shipped to Kennedy on courtesy of the Air Force on C5A. They reassembled it back at Kennedy in another clean room, redid the test to verify that nothing happened along the way, and then installed in the shuttle bay, and launch happened. Once the shuttle clears the launch tower, then the Johnson Space Center takes over the shuttle operations. When the shuttle gets on orbit, they open the cargo bay doors, use the robotic arm and lift Hubble out of the cargo bay. And before handing it over to Goddard for operation and letting the shuttle go home, we wanted to make sure that we establish communication and make sure that the solar arrays are out, because we've got to keep the battery charged. The two most important things for any spacecraft is to keep the batteries charged and communicate. The communication went well. One of the solar arrays went out just fine. The other solar array deployed about halfway, and everybody had to get their heads together to decide what to do. And the universal decision was, let's try again. And we were lucky the second time it went all the way out. So now we're ready to start operations. The Hubble could go home. I'm sorry, the shuttle could go home. Since Hubble is in low Earth orbit, it can't see the ground system all the time because it's going around the Earth and the ground station is fixed, of course. So the main communication path is from Hubble up through tracking and data satellite synchronous altitude. This TDRSS can see its ground station at White Sands, New Mexico all the time. And then there's a hard link from the ground station there to Goddard. So that's the primary communication path. Hubble also has tape recorders on board for times when the communication path is broken and you need to record the science data. The first few months of this and most other spacecrafts dedicated to check out the ground system and the ground to flight interface and all the flight hardware and software. During the checkout, we had two minor problems with the Lockheed portion. One was we had a limit set too tightly in the flight software. So that was one database change in the flight software, so that when we opened the aperture door, it didn't trigger a problem. And no impact on the operations. The second one was a little bit more subtle to troubleshoot. When they were putting Hubble through its paces, one of the gimbals on one of the antennas indicated an overcurrent and shut down. Took a little while with the guys in Sunnyvale to get out the as-built photos and their CAD models, and figured out we were a little too generous on specifying how far the gimbals could travel. So once we found out that was as a matter of a small change in the ground software that limited the gimbal travel. Again, no real impact on the operations. As Hugh talked, during the checkout of the pointing control system, everything was working fine, but we did notice some anomalous disturbances. After looking at the nature of the disturbance and the frequency of the disturbance, that was traced back to the solar array reaction to solar heating. And as Hugh said, they were able to modify the flight software to minimize this. They couldn't make it go away until the solar array was replaced on the first servicing mission. So it was a pretty clean checkout so far. Once the basic spacecraft was checked out, then it was turned over to the science teams to start checking the science instruments and the telescope. And that's when the primary mirror problem surfaced that got all the publicity. It was discovered actually during the checkout of one of the science instruments. They found out they couldn't focus to the degree planned on. Then there was a lot of work with the science team and the Perkin-Elmer Corporation and the NASA team trying to figure out what had caused that and how big is the error. They traced it back to a very subtle error in the test equipment they used to grind the mirror. The mirror was a little bit too flat by a fraction of a human hair out at the edge of the mirror. Once they found out what had caused the problem and how big it was, then they could design corrective optics to take up and install on the first servicing mission. So even though the first servicing mission corrected a lot of things, there was still a lot of significant science that could be done prior to that. If you look on the Space Telescope Science Institute page, you'll see quite a number of papers were written during this time using Hubble data. In summary, this development program here in Sunnyvale was a very successful program. Certainly want to thank all the people who were part of this Hubble program. You made it possible. One key is not only did it work well, but our customers were happy. The last period and also a separate score on the overall contract performance, both were 100% awarded to us by the Marshall program, who was in charge of our contract. So worked with folks to get a follow-on track to provide some operations support to Goddard and some engineering support to the maintenance mission. A third piece of the customer crowd would certainly be the scientists who, the reason for orbiting this telescope. The scientists originally planned on getting about 15 years out of the telescope. It's been up there about 31 years now. So a very successful program all around. Of course, the program itself is continuing, just our piece in Sunnyvale ended in 1990. So with that, I'll bring Cliff Gardner back. He'll talk about what happened afterwards with the servicing missions and a little bit of the science that came from the Hubble. But again, I would refer you to the Science Institute for that. So Cliff.
Thanks, Jim. It really was an interesting program that we were fortunate to work on. I'm going to talk about the shuttle servicing mission and some of the observations made, as Jim said. Prior to launch, spares were built and tested to be used for in-orbit servicing. There were approximately 125 units that can be replaced in orbit. No units were designed to be repaired in orbit. Jim showed you a cartoon breakout of sort of how those boxes could be installed and removed. Orbit replaceable units were designed to operate in spec for 2.5 years in orbit with a probability of 3 sigma. The maintenance operations were designed so that it would require a 1 5/8 inch socket wrench to do all of the maintenance operations. However, NASA built over the years several hundred tools with 5/8 inch sockets to simplify maintenance operations. This again shows the astronaut, as I showed you in the earlier chart, the astronaut doing in-orbit maintenance on the first maintenance mission. The first servicing mission was launched on December 1993, 3 years, 7 months after launch. 5 spacewalks were required. The operations they did was they removed the wide field planetary camera and installed the wide field planetary camera 2. Wide field planetary camera was considered the primary instrument of the 5 in the observatory. The high-speed photometer, which had completed 95% of its science and was virtually unaffected by the anomaly on the mirror, was removed, and the corrective optic space telescope axial replacement was installed. They called that the CoStar. And the CoStar had 5 pairs of mirrors that could be moved into and out of the focal plane for the faint object camera, the faint object spectrograph, and the high-speed spectrograph. 2 rate sensors were changed out, 2 magnetometers were changed out, 2 gyro electronic control units were changed out, and the astronauts installed the Goddard High Resolution Redundancy Kit and installed a coprocessor for the DF-224. The second servicing mission was launched on Shuttle Discovery in February of 1997, 6 years and 9 months after launch. 5 spacewalks were required. The faint object spectrogram was replaced by the Space Telescope imaging spectrograph. The high-speed photometer was replaced by the infrared camera and multi-object spectrograph. One of the fine guidance sensors was changed out with an upgraded fine guidance sensor. Optical control electronics enhancement kit was installed. One of the engineering science tape recorders was removed and they installed a new solid state recorder. One of the other engineering science tape recorders that was not performing correctly was replaced by a spare engineering tape recorder. One of the reaction wheels was replaced. The data interface unit 2 was replaced, and they removed the solar arrays that they had. They removed one of the solar array drive electronics and replaced it. This third servicing mission was launched on Shuttle Discovery in December of 1999, 9 years, 7 months after launch. 3 spacewalks were required. Note that I said December of 1999. It was in late December that it was launched. The fine guidance sensor was replaced by a refurbished fine guidance sensor. This was when Hugh talked about where they removed the DF-224 computer and installed the Intel 486. They also installed replaced a digital data recorder with a solid state recorder. One of the S-band transmitters was replaced, and they installed a 6 voltage temperature improvement kits. And they also replaced one of the rate sensors. They had a couple optional servicing mission operations that they wanted to perform. However, those were specified as optional because they wanted to return the shuttle to ground prior to the end of the year, so they avoided any concern over the YK2 issues. The fourth servicing mission was launched on Shuttle Atlantis in March of 2002, 11 years and 11 months after launch. 5 spacewalks were required. The European Space Agency faint object camera was replaced by European Space Agency Advanced Camera for surveys. They removed the solar arrays that they had installed and replaced them with rigid solar arrays that were state-of-the-art. These arrays were smaller, but they could generate 20 to 30% more power. The power control unit was replaced. It was an updated power control unit that would be able to take advantage of the increased power. They installed a near-infrared camera and multi-object spectrograph cooler on the infrared camera. They replaced one of the diode boxes and they replaced one of the reaction wheels. Next, please. The fifth and last servicing mission was launched on Shuttle Atlantis in May of 2009, 19 years and 1 month after launch. 5 spacewalks were required. The Wide Field Planetary Camera 2 was removed and replaced with Wide Field Planetary Camera number 3. The co-star was removed, it was no longer needed, and they installed the Cosmic Origin Spectrograph. And then these astronauts did some amazing things. They repaired 2 of the scientific instruments in orbit. As I mentioned earlier, that it was not designed to do that. And they had, in their gloved hands, they had to remove the covers on the scientific instruments, do some rewiring and replacement of some of the electronics in them. When they powered them back up, they found that they were operating amazingly well. 6 rate sensing units were replaced. One of the fine guidance sensors was replaced, and the 6 nickel cadmium batteries that had been operating for 19 years, kind of like the energy bunnies, were replaced with 6 new nickel cadmium batteries. The scientific instrument control and data handling unit was replaced with an upgraded scientific control and handling unit. They also installed a soft capture mechanism on the exterior of the telescope in order that in the future, someday, if they wanted to retrieve the Hubble, they could use that to attach to it. This shows an image of the astronauts getting ready to do an in-orbit maintenance on the aft section. You can see they're on the remote manipulating system of the shuttle. This is an astronaut installing the Wide Field Planetary Camera. It's pretty amazing. It's a heavy object, and there he is installing it by himself with some guidance from another astronaut. Now I'm going to talk about 30 years of discovery. Significant observations that were made by Hubble during science. I'm going to give you some examples. They obtained data on the expansion rate of the universe, which was really an amazing feat and something that they were really interested in being able to do. They made a lot of investigations of our solar system. They observed how stars form, live, and die. They observed intricate shapes, structures, and histories of galaxies. They discovered massive black holes and found that black holes were everywhere in space. This image is called Hubble's 30th anniversary image. And every year, the Science Institute would select an image that they thought was of significant interest to the public and issued that as their anniversary image. This is called this observation shows a giant red nebula and a smaller blue nebula that are part of a star-forming region in a galaxy satellite of the Milky Way. The nebulae are 163 million light years away. This is an observation that's called Mystic Mountain. It shows the activity at the top of a pillar of gas and dust. The pillar is 3 light years tall. It's being eaten away by the brilliant light from nearby stars. Infant stars inside the pillar fire off jets of gas that can be seen streaming from the towering peak. Some additional discoveries that they made, they got a lot of additional information on as yet unexplained phenomena called dark energy. They're also using land-based observatories to gather that information. They have made an observation of a dull star that suddenly became 600,000 times more luminous than our star. The star has since faded. They were able to gather significant new information about our moon's crust. They made the 1 million second observation of a patch of sky, 1/10 the diameter of the moon. That's the image that Hugh was talking about. This image is called the butterfly emerges from stellar demise. The observation is of a planetary nebula. What appears to be butterfly wings are heated gas to nearly 20,000 degrees Celsius. The gas is tearing across space at about 950,000 kilometers per hour. In the center of the dying star, once about in the center is a dying star, once about 5 times brighter than our sun. The star is ejecting gases and is unleashing a stream of ultraviolet radiation that is making the cast-off materials glow. This image is 380 light years away in the Milky Way. Next, please. This image is called the lightsaber. It's really an interesting image. The lightsaber appears to slice through the dark clouds of dust and gas that have surrounded it. The 2 beams of saber-appearing light shooting out from the star at supersonic speeds are formed by material falling out of the newborn star. Sometimes clouds of dust always create new stars as they fall inward. In this case, the materials streaming in erupted into fiery jets. Additional information that was gathered was detailed data on the expansion rate of the universe. They created an album of galaxies to observe their evolution. They observed planets on other stars and were able to actually analyze the environment of those planets. They observed planets forming in dust disks around stars. They observed galactic details and mergers. Next, please. This image is called a rows of galaxies. The shape of the larger of the 2 galaxies shows signs of tidal interaction with the smaller one. Astronomers believe that at some time the smaller galaxy passed through the larger one. The little jewels, blue jewels at the top, are the combined light of clusters of intensely bright and hot and young stars. Next, please. This image is called the antenna galaxy unloaded. The observation is of 2 galaxies locked in a deadly embrace. They were once normal, sedate, spiral galaxies like the Milky Way. The pair have spent the last several 100 million years clashing with one another. The clash is so violent, the stars have ripped from their host galaxies to form an stream of arc between the 2. The far-flung stars and streamers of gas stretch out into space, creating long tidal waves reminiscent of antennae. There are clouds of pink and red gas around the blue flashes that are forming new stars. Eventually, these 2 nuclei will merge and become one. In summary, one Hubble contract requirement was to operate for 15 years with a servicing mission every 2.5 years. Hubble continues to operate 31 years after launch with only 5 maintenance missions. The last one was performed 11 years ago. Hubble is expected to remain operational in as gradually reduced state for another 9 years. Another Hubble contract requirement was to detect images 2 billion light years away. Hubble has made observations of images more than 13 billion light years away. Hubble made the 11-day observation of a patch of sky 1/10 the diameter of the moon. All Hubble servicing mission operations were successfully performed. The Space Telescope Science Institute has made over 30 years of observations. 1 day of observations fills the equivalent of an encyclopedia.
So it's time for the panel's discussion. If everybody appropriately turns on their cameras. We have a bunch of open questions here. Cliff K, are you going to read them, or am I going to read them?
Well, I can read some and then you can take over. Let's see where we start.
Let me start with one I was in the middle of answering online. There's a double question. Where could I learn more about the mission? And I said the NASA Goddard site and the Space Telescope Science Institute site. And the person also said, how can I reach your group? Tom, do you have an answer for that one?
Yes, I gave the URL, www.siliconvalleyhistory.org.
Okay.
Or if you just look, Google IEEE Silicon Valley History Technology Committee, you'll get all sorts of links.
The answer.
So Tom?
Yeah, Cliff?
Yeah, I'll just go down the questions that were answered, but perhaps were delayed till now. And there were a few of them. And I'm going to start at the top unless you have another activity.
I think you starting at the top, it would work fine.
Okay. One question, anonymous attendee, has the Hubble ever faced problems in space? I'm not sure what the intent of that question is, but maybe the panel can jump in. Problems in space. There you go.
Well, to start with, there were the minor problems we had during checkout. And of course, during the course of Hubble, in between servicing missions, there were failures of hardware. And as Dr. Dougherty talked about, for example, when fewer than 3 gyros were available, they came up with a system to be able to operate with fewer than 3. Now, you don't get full capability until you get the next servicing mission up. So yes, there were problems. There were none that I'm aware of that were catastrophic in the sense that they were worried about losing the spacecraft. Hugh, you may have some more insight into that.
No, I think, Jim, that you said the thing, no one's looking for problems and no one found problems. So, I mean, anything was that there was a problem showed up and people took care of it. So,
Well, let me jump to one of the other questions. I think it's for you. Was the gyro design unique for the Hubble, or is it based on a previous design?
well, it was a platform gyro that was used by MIT on the guidance systems, actually Polaris, and there was a torquer put on it to make it a strap-down gyro. This gyro has been around a long time. Goddard's used it on some of their space missions, you know, and we, you know, adapted it for our use. So anyway, it's been around a long time as a gyro. The operations have been well documented by other people, like the Goddard efforts.
I
I
think,
think you could almost trace it back to V2 rockets if you tried hard enough. Okay, this is a good question here because I don't know the answer, and it's curious. What is the orientation of the 4 reaction wheels? Are they oriented like the 4 sides of a tetrahedron?
Well, they're oriented like the ribs on an umbrella, so that they put 30% of their torque and momentum into the V1 axis and the other 70% into the V2, V3 focal plane of the system. They're not a tetrahedron.
Yeah, well, it's a good question though. Okay, there was a question about KH-11s. You know, that's not something that anybody wants to discuss. I think we got to move past that kind of thing. How much longer can Hubble remain operational?
Well, if you listen to there was the thing you sent me, which was the video put together by the stock ground station, and they said they're confident they can make it to the 1930s.
Yeah.
So I mean, I don't think the ground station sees a
2030.
problem, and they're closer than any of us. You know,
I think you mean 2030s.
I have another
2030. I'm sorry. Yeah.
Another question just came in on the same subject. Could a future maintenance mission extend the Hubble life even further? Is one possible? If so, when?
well, the maintenance missions were all predicated originally on using the shuttle. And of course, there is no more shuttle. So could they do a maintenance mission with a robotic mission? Not very likely. They'd need another manned mission. So we'd be speculating on that. I would suspect the answer is no. Anybody else got a comment there?
I agree,
Well,
Jim.
I'd say nobody's building hardware, so there's nothing to bring up. So unless they start a contract to start an effort on the ground, doesn't make a difference to have anyone else to go up.
Here's a question that Tom Gardner answered. I'm not sure of the answer, so I'll ask you, Hugh. What is a PID?
Proportional integral derivative. It's a
Okay.
proportional gain plus an integral gain plus a derivative gain.
It's a control system question that I certainly should know the answer to, right?
Yeah,
Shame
All
on
right.
you
you.
took my class.
Yes, I did. I knew that was what the the nature of the answer should be, but I didn't have it at my fingertips. Let's see, we got some more open questions. Vibrations and liftoff. Well, okay. If you want to answer that, anybody?
Well, I
What
think
about vibration and liftoff?
Yeah,
during liftoff, there are some vibrations. Now, the Hubble was tested in an acoustic chamber where they blasted it with much higher vibration levels, sound levels than it had on the ascent. And on ascent, the Hubble is not live as far as controlling anything. It's basically just a payload. In fact, the only thing we had once they closed the shuttle bay doors, the only observation we could see was what was the temperature in the cargo bay. But it had seen, as a matter of test, much higher vibration levels than experienced in ascent.
I mean, also the black boxes all have to go through a qualification test where it puts them on a shaker table and they have to get excited that way. So they get a lot of it shaking to rattle and roll before they go.
In the acoustic test, it was subjected to 135 dB for 2 minutes.
Here's one here. What aspects of Hubble are the most outdated with respect to current technology?
I would say it's the computer technology, because in 2004, the scientists wished they had a new computer up there, but that's typical of all the missions, because even the Voyagers have old computers and the scientists are complaining about that. But their comment was it's better to have something to work with that they can use. We can't update everybody's technology. I would say the gyros and the reaction wheels and all the other pieces of the hardware are pretty current, state of the art. There's no one's got something as good as them.
Here's one that I think I can answer. Does anyone have the capability of mounting a service mission to the Hubble? And the answer is Elon Musk, amongst others. The question is, does he want to?
Well, someone got to pay him. Someone got to fund it. God is big on using automata, and not using people. So if they could do some kind of an automata mission where they sent a robot up, that would be more the direction that they would be willing to fund.
There was some question here, and it was asked twice about the shipping of Hubble to the Cape from Lockheed in Sunnyvale. What I see here, somebody has written, is that there was a barge channel behind Moffett deepened for a seagoing barge. Has anybody ever heard of that? And then with the Challenger disaster, somehow a C5 became available and ready to ship Hubble. Any clarification?
Well, originally the barge shipping to the Port of Oakland and picked up by a ship down through the Panama Canal was the original plan. But by the time it got around, the Air Force had developed a generic shipping container that would fit on a C5 to ship from any place to either Vandenberg or to Kennedy. That was done back when there was the thought that all future large payloads would be shuttle compatible, and they would stop using expendable launch vehicles. So that was available then. That wasn't available when the contract started.
Here's one. What are the main failure mechanisms of the gyro? Bearings, hydrogen helium leak? Do they even have hydrogen helium? Anything else?
Yeah. Well, the thing that's failed, and I hate to say failed, but the thing that happened is that the bromide fluid is very corrosive, and I'm just telling you what I read, because this was something that came up way late here. But the idea, what they think now, is that there's like 10 mil silver rings that strips that go between the housing and the float, and it carries the current. And the thought is that what had happened is that somehow oxygen had gotten into to that area into the bromide, and it caused a corrosive action. So all the gyros now are filled in a helium, nitrogen atmosphere. So I mean, that's the only mode that anyone's seen that really as close a failure mode.
Cliff, you can read a question?
Sure. Here's one. The question is how station keeping on Hubble is performed. I assume that's got to do with orbit degradation or something like that, but I'll let the panel answer.
There is none. I mean, there's no propulsive mechanism on it. That's like, I think Jim was saying before, they boosted it at 380 miles and it's down about 330 now. And it keeps dropping down. It'll eventually be pulled in by the atmosphere. And that's why they put the ring on it, so that someone could be contracted to go up and grab onto the ring and bring them back. Probably stick them in the ocean, actually, but that's what they're going to do.
Yeah,
It's coming down.
Yeah, every maintenance mission, I believe, they did boost back up to make up for the accumulated drag. But since there is no more shuttle, it'll have to be a robotic mission of some sort to go up and fire retro direction, and like Hugh says, probably into the deep ocean.
Here's a question. Has anyone compared the cost of orbital servicing with the cost of replacement? If orbital servicing is so attractive, why hasn't it been adopted by the military for reconnaissance satellites?
Well, part of the answer is designing something that's serviceable is very expensive, and mounting shuttle missions to go up is very expensive. I think back when, just my opinion, back when when Hubble was first conceived, that was the time frame that the plan was to have shuttle launches very cheap and have very often, and they'd be able to go out of Vandenberg and out of Kennedy. Well, that never really happened, and I think after that, that was a big reason. It's not cost effective.
Here's a question that really didn't get a good answer. Somebody was wondering about CCDs. So essentially, it's an electro-optical question. What was put on the original? What was put on the original telescope to sense, light, essentially, and how good was it?
Well, there was nothing on the spacecraft. That's why we used the interferometer. They used photomultiplier tubes. So the only one who uses CCDs was the scientists, okay? And, obviously that's why there's the wide field camera 3, right? Because that uses the latest technology they could get at that time, going up in 2009.
The original,
but there are actually no CCDs. Yeah.
The original wide field camera and the original faint object camera, I believe both used CCDs that would have been a vintage of 1980s vintage. But of course, as technology increased, that's why they replaced the instruments. And of course, when we had the Challenger disaster in late 80s, all the science instruments were pulled off and were updated for later technology.
Here's a question comparing the Webb to the Hubble. What's going to happen to the Hubble after the Webb gets deployed?
Well, the intent, as I heard, is to keep it going as a complement to each other, because each one can see different wave bands. And, so Hubble will go until they decide they don't want to fund it anymore, because there's no way that the Webb can see above the IR. It's basically an infrared telescope. They're looking for those galaxies that are moving way away from us, okay? And we see the ones that are closer. I think it's like that composite picture I showed. They basically take the data from all the spacecraft, all the satellites, and put it together into composite image to see how much they can learn about astrophysics.
Here's kind of a two-part question. I guess it's a compliment to the speakers. Clearly, says the questioner, we heard from first-rate engineering managers. That's you guys. I second that or third that. I think the rest of the question is, what lessons should we learn from Challenger and Columbia? And what the questioner says here, Perkin-Elmer's totally inaccurate manufacturing of the primary mirror. I guess I would, that if that's a perception that the public has, it probably needs some correction somehow. So I don't know if anyone wants to comment on that, but my understanding is a very, very, very subtle error.
Well, the point is there's books written on this. So if you want to know about it, read the books. And
There you go.
those are panel discussions. I mean, people have looked in depth at what the problem is, and we would just be kind of, hitting the surface,
Yeah, and I think certainly, I've seen a lot of that information is on the web that has detailed explanation, and you really need to be an optical engineer to understand it. I don't understand it. I've looked at it, but there were no hidden agendas there, but they published everything that they found.
So how much
I have a comment on the James Webb versus Hubble. Hubble looks in the visible for the most part, and the James Webb looks in the infrared. So I think those are complementary capabilities rather than the James Webb being a complete replacement for the Hubble. But that's about all I know. Any comments on that? I think they overlap.
Didn't somebody tell me that one of the challenges or problems with the web is that it has a limited life in the IR because it's a consumable material?
No, I made a mistake when I said that. It really hides behind a shade and it goes to 50. But the lifetime they predicted or hoped for is 5.5 years. But it's like Hubble, it can keep going if nothing fails.
So how much did the prior Lockheed experiences on the KH-11 and earlier satellite construction experience help the Hubble design? I think each of you can probably comment on that, since you all were with Lockheed before that.
Well, you had to work on the program you had mentioned. So I worked mainly on high altitude programs and a few other things like that. So we went over with the experience I had. So that it's not clear that anybody took anything off of any of the programs and brought them along. I mean, Bill, I think Jim mentioned the Agena. Jim worked the Agena. I was sort of at the tail end of the Agena, but the other programs that maybe most of us were not on.
Okay.
I think the test equipment crew had been on other things, and of course we'd use the test facilities. And I mentioned the computer and the computer hardware we already had, but everything else on Hubble was very unique. Now, the experience of people like Hugh were invaluable on coming up with. He had worked on digital control systems before, even though this one was totally different. So I think they brought the experience, but not really any design per se.
Another question for each of you is, what's your favorite image from the Hubble? Cliff,
I like the butterfly.
you like the butterfly. Jim, do you have a favorite?
I don't think so. Hugh might. Probably the one
No,
he showed there.
Well, I put that up because it was there, but I think there's so many pictures. If you're into astrometry, I don't think there's one that's favorite, because each one always shows a different facet of the astrometry. So I don't. It's not like you're taking a picture of your favorite baseball player or something. So.
I think one of the first ones that I liked was the very early pictures they had of Saturn. You got an up close look at the rings. That was more of I believe, more of a publicity photo than a hard science, but still it was kind of an interesting picture. That came out very early in the mission.
Well, we're starting to run out of questions. We've got several compliments, and it's coming up on 2 hours. So unless Cliff,
A couple of open questions. I see one about the there are pictures that are published that have jagged shapes in the outline. I believe that's, Hugh, you can probably correct me. I believe that's cases where those are sewing together multiple images at different times. And so you end up with different size pictures that you're piecing together. Is that correct?
I don't know if it's correct, but I think that's the idea. I mean, we have dropped the resolution down. You know, we can command such small torques and sense such rates that we basically eliminated any of the characteristics of the control system that can be seen in pictures. We're well below the resolution to figure that out.
Right. Yeah, I think the picture, the jagged edges they're talking about in the question, I think are the ones where they've pieced together several different photos. And so you end up with different field of view on the different photos.
I have to fess up to a mistake that I made on the 5th servicing mission. I knew the correct answer and somehow it didn't get changed, but the batteries were actually nickel hydrogen and not nickel cadmium.
Nickel hydride?
Nickel hydrogen.
Okay. Okay, well, I think it's probably time to end this webinar. I really appreciate the efforts that Jim, Cliff, Gardner, and Cliff and Hugh put into their presentations. The presentation is available on YouTube Live on my channel, and ultimately it'll be cleaned up a bit and posted at the Technology Histories website. Thank you guys, and thank the audience for staying with us. It's been very informative.